So, today we will discuss fundamental theorem of integral calculus that requires the concept of a indefinite integral. So, before starting the fundamental theorem, let us see the indefinite integral. Let us suppose f x is, we bound it, that f x be bounded and Riemann integrable in the interval say a b, closed interval a b. Then the integral a to x f x dx, a to x f x dx, where x is a point in between a b, is known as the indefinite integral, is known as indefinite integral of the function f x, of the function f x, and is a function of, and it is a function of the upper limit of integration, upper limit of integration that is here upper limit is x. So, we denote this thing as capital F x. Okay. So, it conveniently to denote this expression f x as indefinite integral a to x f x dx, where f x we call it as a indefinite integral of the function f x, which is a function of the upper limit x. So, x changes, the corresponding f x will change. In fact, the behavior of the f x depends on all x. So, first result which is valid for the indefinite integral is that if the function f x is bounded and Riemann integrable in the interval a, then function f x will be a continuous function. So, f x is a continuous function of x in the closed interval a b, where it is also absolutely continuous function, absolutely continuous function in the closed interval a b, in this interval a b, absolutely continuous, where f x is bounded and Riemann integrable over the interval a b. This is okay. The proof is not that difficult. Let us consider f x plus h minus f of x, capital F x plus h minus capital F x. This is equal to what? A to x plus h f x dx minus a to x f x dx by definition, and this will be equal to what? X to x plus h f of x dx, because of the Riemann integrable properties of the Riemann integral functions we get this. But this m dash given function f x is bounded, okay, and let in the interval a b, closed interval a b, and let m dash m be the least upper bound of the function f x mod f x over this interval a b. Let it be this. Then the f x plus h minus f x, this can be written as f x plus h minus f x is less than equal to capital M times into length of the interval say h. So, it can be made less than epsilon when h is can be less than h is less than epsilon by m. It means the difference of this can be made less than epsilon when h is sufficiently small. So, when h tends to 0, limit of the f x plus h will go to f x. So, this shows f is continuous. F x is continuous from the right, continuous from the right, is it not? So, continuous from x plus from right, but the same result hold if I take x minus h, then f x minus h, here the difference will come only this. So, what we get? We will get only thing is that this x plus minus h, when you take the modulus of this, sorry, it is modulus of this, then there is no change, you will get f dash h, and which gets to that. So, this is continuous at the point x, at x in the interval a b. So, this integral this indefinite integral f x is a continuous function of x. Second result is that second part, it is absolutely continuous. F x is also absolutely continuous function. So, f x, second part of this, f x is also absolutely continuous, absolutely continuous function in the interval a b. So, absolutely continuous function means this is the interval a b. If I picked up the say intervals a1, b1, a2, b2, an, bn and so on, such that the sum of this is h less than h, then the images of this f of x at this point b I minus f of x I is will be less than epsilon. That is what we wanted to show. So, let us consider let a1 b1, a2 b2, an bn and so on. These are the infinite be a finite or countable set, finite or countable set of non-overlapping intervals of total measure that is the length is less than h, that is sigma of b r minus a r, r is 1 to infinity, is less than h. Then we have the sigma of mod f of b r minus f of a r, r is 1 to infinity. Now, this will be less than or equal to what? Integral of this part, that is integral sigma r is 1 to infinity and then integral a r to b r f of x dx, and which can be written as less than or equal to, because mod of this is there. So, modulus of this. So, this is less than or equal to sigma r is 1 to infinity m times of this, mod of this is m. So, we can write m into mod of b r minus a r, but this is less than h. So, we get this is less than m h, which is less than epsilon r when h is less than epsilon by m, where m is the maximum or the least upper bound of the function mod f x over the interval x lying with this. Okay. So, this is what we. Therefore, this implies the function f x is absolutely continuous function, absolutely continuous function in the interval a b, and that proves the result. Okay. Now, after getting we get now the first fundamental theorems of calculus. So, first fundamental theorems of first fundamental theorem of integral calculus. The theorem says like the theorem says at a point of continuity of the function f x, the function capital F x, that is the indefinite integral capital F x, is differentiable and the derivative is equal to f x. So, let us see the now in case if okay. Now, what is given is the function is continuous. Let f x is continuous at a point x I belongs to the interval a b. Suppose. So, limit of this function f x as x tends to x I is the same as f of x I, or that is we can say for any epsilon greater than 0 we can write the f x lies between f x I plus epsilon and f x I minus epsilon by definition of this. So, this f x lies in this interval, in the interval x I minus x h x I plus h, that is when x lies between in this interval, then f of x will lie in this interval by definition of the limit. Okay. Function is continuous, we can for given epsilon greater than 0 we can identify the h, so that the all x which lies in this interval, the corresponding f x will lie in this interval. So, this is by definition. Okay. Now, consider this f of x I plus h minus f of capital F of x I. Now, this will be same as x I plus h by definition f x, just by definition of the antiderivative in this indefinite integral we can use this. Now, this f x lies between these two bounds. So, obviously, this interval will lie between the so this integral which lies between what plus h f x I plus epsilon and h f x I minus epsilon, because f x lies between these two bonds. So, length of the interval is h. So, this value of this integral will lie between these two bonds. Similarly, when you take minus sign, you are getting this minus x I minus h. So, it will lie between the plus minus this interval, plus minus this, that is all. Okay. So, divide by this. Therefore, when you take the f x I plus a f of x I plus minus h minus capital F of x I divide by plus minus h, okay, then it lies between what f x I plus epsilon f x I minus epsilon. So, limit of this when h tends to 0 is nothing but the f of x I, and this limit is equal to what? The derivative of f prime at a point x I. So, if the function is continuous at this point, then the derivative capital F x will be differentiable at that point, and derivative of the capital F at this point coincide with the functional value at the point x I. That is what we have shown. Okay. Now, as a remark we can say Now, the xi is an arbitrary point, it's clear. Xi, so at any point of continuity, the function f x is differentiable and derivative is equal to f x. So, this can be shown. Okay. Now, remark we can say, given that function f x is Riemann integrable, since f x is Riemann integrable, so the necessary sufficient condition for the Riemann integrable is the function must be continuous almost everywhere. So, this implies f is continuous almost everywhere in the in the interval a b, say a b, okay, in the interval a b, and f x is continuous almost, so the corresponding indefinite integral capital F x will be differentiable almost everywhere in the interval a b. So, this implies that the function capital F x possesses a differential coefficient equal to f x almost everywhere in the interval a b, almost everywhere in the interval a b. This is the first remark. Second is, in case if f x is continuous throughout the interval in the closed interval a b, then the definite integral capital F x has a differential coefficients throughout the interval a b, which is equal to f x. So, this two remark is very interesting, important, in fact we get. The third remark we can say, at the point of ordinary discontinuity, if f x has a point has an ordinary discontinuity, at a point say xi, say x naught in the interval a b, then ordinary discontinuity means that left hand limit and right hand limit exist but may not be equal. Then in that case the function, then it can be easily shown that the function capital F x has left hand and right hand derivatives, and these are equal to f x say x naught plus epsilon r and f of x naught minus epsilon r respectively. Now, at the point of second kind of f x, of discontinuity of second kind of f x, it means the function is not defined at this point, the capital F x need not have derivative on either side. So, this, okay. So, this we get it. Now, the concept of the primitive, or it is also known as antiderivative. Antiderivatives, primitive or antiderivatives. Any function phi x which possesses a differential coefficient equal to f x at every point of the interval a b in which f x is defined. Is said to be a primitive or antiderivative of f x. So, what it says is, suppose f x is a function f phi x is such that its differential coefficient coincide with f x at every point, then we say phi x is an antiderivative of f. For example, if I take the sin x, phi x is suppose sin x, then f x is say cos x. Okay? So, minus sin x, this function is an antiderivative of cos x, isn't it? Because the derivative of this sin x, this is plus. Derivative of this sin x coincide with f x. So, it is sin x will be antiderivative of cos x, like that. So, similarly, we can get another examples or like this. So, now this antiderivatives may not be unique. In fact, we have the antiderivative of the function of f x of the function f x is not unique, because if f phi x is an antiderivative, of f x, then phi x plus constant k is constant, is also an antiderivative of f x, because derivative also coincide with phi x. So, it is not unique in nature. It is, if function is antiderivative, then constant plus that function will also be an antiderivative. Yes. Now, we have based on this, we have the second theorem, which is known as the second fundamental theorem of integral calculus. Second fundamental theorem of integral calculus. What this theorem says is, if phi x is a primitive of a is an antiderivative of f x, and f x is continuous in the closed interval a b, then a to x f x dx is equal to phi of x minus phi of a. Okay. This is also known as the Newton's formula, of course. So, that we will see. Okay. Then f x is continuous in this. Now, let us see the proof of it. Proof is now f x is continuous, since given that f x is continuous in the interval a b. So, the function capital F x, which is a to x f x dx, is an antiderivative of f x. This we have already proved. The derivative of f prime x is coincide with f x. So, it is an antiderivative of this. Okay. Let us suppose phi is another antiderivative, but what phi is already given. Phi is given as an antiderivative of f x. So, what the result? If phi x is antiderivative, then phi x plus constant will also antiderivative. It means the difference between phi x and f x must be a constant. So, this implies that f x minus phi x, that it has a derivative, this has a differential coefficient at every point of the interval a b, in the interval a b, open interval of course, which is 0. Why? Because the derivative of this is f x, derivative of this is also f x. So, this function has a differential coefficient at every point, and the value is 0. Therefore, this implies that the function f x minus phi x must be a constant function, in the interval a b. But what is f of a? F of a is 0. So, if I substitute here x equal to a, so from here we implies that minus phi a is constant. That is, f of x comes out to be phi x plus constant. So, constant means phi of a. So, that proves the result for it. Okay. So, that is equal to f x, and this completes the proof. Okay. Now, in this case it is not necessary, remark or note, it is not necessary for that for the truth of the theorem, that f x should be continuous. In fact, if it is a Riemann integrable function, continuous throughout in the interval a b. In fact, if function f x is bounded and continuous almost everywhere in the interval a b, that is f x, this closed interval, in the interval a b, that is the function f x, if f x is Riemann integrable function, in the closed interval a b, then the integral a to x f x dx is nothing but the phi x minus phi a, where phi x is the primitive, is antiderivative of f x. Okay. Clear? So, that is what is. Now, this theorem we call it a second fundamental theorem in calculus. Now, there are certain cases. Remark, what is the difference between the primitive, antiderivative and indefinite integral? The difference In fact, they are not the same. The indefinite integral difference between indefinite integral and primitive, because indefinite integral is also a primitive, because its derivative coincide with this, and primitive by definition those functions whose derivative coincide with f x is the primitive. So, some may think that both are basically they are the same concept, but this is not so, they differ. Definitely we will give an example where the function has an indefinite integral, but primitive does not exist. Similarly, the function has a primitive, but indefinite integral may not exist for it. Okay. So, we can give this only what first remark is difference. These two concepts, first point, these two concepts are distinct, they are not same, two distinct concepts. In fact, the indefinite integral and primitive are two distinct functions. Okay. Distinct function. When f x is continuous, when f x is continuous, f x is continuous in the closed interval a b, then the indefinite integral is also its primitive. But even then the primitive is not the indefinite integral. Okay. Is not the indefinite integral. In fact, primitive is not the indefinite integral. Okay. So, example let us see. F x has no primitive such that this. Okay. Let us consider the function f x, which is 0 when x is not equal to 0 and equal to 1 when x is equal to 0. Let us see. Now, clearly f is Riemann integrable. Why? Because it is discontinuous only at one point, because it is continuous everywhere except at point everywhere except at the point x is 0, which has a measure 0. So, it is almost continuous function. Therefore, this and the value of this integral 0 to 1, value of this integral f x say I say 0 to 1, integral 1 f x dx is 0. Just I take the interval 0 1. Okay. But what is f x? But f x, so f is integrable. So, this shows f is Riemann integrable function and value is 0, but f x has no primitive. No primitive, because we cannot get any function phi whose derivative coincides with f x, because if we take phi x to be constant, derivative will be 0 fine, but at the point 0 the derivative is not coming to be 1, and if we want the 1, so phi x must be x. So, again the phi x is x, then it must be derivative will be 1, but it cannot be 0 for other points. So, we cannot find the primitive. So, the function is Riemann integrable, means it is indefinite integral exists, So, that is the f is has a indefinite integral, but it does not have any primitive. Okay. Another example let us take this function f x, which is x sin 1 by x square minus 1 by x cos 1 by x square, when x is not equal to 0 and equal to say 0 when x is 0. Now, this function is not integrable. Why? F is not Riemann integrable, does not belong to the Riemann integrable function, does not Riemann integrable. Why? Because f is unbounded at the point x is 0, nearby in the neighborhood of 0. Neighborhood of 0, this goes very frequently up and down. So, it is not bounded function, f x is unbounded. So, therefore, it cannot be Riemann integrable function. But the phi x exists. Phi x, if I write like this, x square by 2 sin 1 by x square by 2 sin 1 by x square, when x is not equal to 0 and equal to 0 when x is 0. Now, if we take this phi, then clearly the phi dash x coincide with f x. So, phi is the primitive, but Riemann integral does not exist. So, phi is primitive, which is primitive of f x, okay, but it is not Riemann integral. So, this shows that we get it. Now, there are two mean value theorem which we will just state, and of course, mean value theorem. The first mean value theorem is theorems. The first theorem says if f x g x be bounded and integrable in the interval a b, and g x maintains the same sign in the interval a b, then integral a to b f x g x dx is mu times a to b g x dx, where mu lies between the greatest lower bound and least upper bound of the function f x. Okay. In particular, when f x is continuous, in the interval a b, then integral a to b f x dx equal to f of xi a to b gx dx, where for some xi lying between a to b. Okay. Let us see the proof of this. So, what is given? F and g be a bounded function. Let f x and g x be a bounded function and integrable in the interval a b, and g x maintains the same sign. So, let us suppose let m and capital M be the least upper bound with the greatest lower and least upper with the greatest lower bound and least upper bound of the function f x. So, the value of the f x will lie between m and capital M. This is clear? There is nothing. Okay. since gx maintains the same sign, either it is positive or it is negative. So, if gx is positive, so when gx is greater than 0, then we have this multiply by gx both side, we get the same fx gx, which is less than equal to m fx gx, f m capital Gx, and when Gx is negative, then the order will reverse. So, we get m of Gx is greater than equal to fx g of x, which is greater than equal to capital M Gx, like this. Therefore, integral a to b fx g gx dx, this integral. So, this integral will lies between m gx, m integral a to b gx and dx, and capital M integral a to b gx d. Either this will be the lower bound when this is positive, or this will be the lower bound when it is negative. So, it lies between these two one. But f and g both are giving to be what? Riemann integrable functions, is it not? So, there will be some point, it means everywhere the integral a to b f x g x, this limit exists, the Riemann integral exists. So, there will be some point where the value of this, but that is a to b f x g x dx will be some constant times mu into a to b g x d. Okay? So, we get this integral is possible, where mu lies between m and capital M. Clear? So, that is just by now. In case if f is continuous, then this mu can be replaced continuous in the interval a b, then there exists a xi in between this such that mu becomes f of xi. So, we get the result, that is proved. Okay. So, this is the first theorem, mean value theorem. The second mean value theorem, we can get it from this result, which is known as the Bonnet's theorem. We will not prove it, just a statement of the Bonnet theorem says, if f x is bounded and integrable and g x is positive, and monotonic decreasing in the interval a b, then integral a to b f x g x dx is g of a to xi f x dx, where xi lies between a to b. Now, if gx is positive, and monotonic increasing, then integral a to b f x g x dx is equal to g b integral xi to b f x dx, where a is less than equal to xi, less than equal to b. Now, this theorem will be used in proving the establishing the mean value theorem, second mean value theorem, and this we get the second mean value theorem. The second mean value theorem, it is also known in the Weierstrass form, we say in the Weierstrass form. This is known as the Weierstrass form. Okay. But this theorem says is if f(x) is bounded, f(x) is bounded and integrable, okay, bounded and integrable, and gx is bounded and monotonic in the interval, closed interval a b, then integral a to b f(x) gx dx is equal to g of a integral a to xi f(x) dx plus g of b integral xi to b f(x) dx, where a is less than xi, less than equal to b. Okay. The proof is use the Bonnet theorem. Use Bonnet's theorem to prove this result. Okay. So, what we say, if our function g is monotonic decreasing, case 1, let g is monotonic decreasing function, okay, then this gx minus gb will be positive, is monotonic decreasing, and positive, because monotonic decreasing means it has a value at the point A is the highest and B is the lowest. So, we are taking gx minus gb is always be positive and monotonic and have the same sign, of course. Then therefore, integral a to b f(x) gx dx, this will be equal to ga integral a to xi f(x) in fact, this is f of gx minus gb dA. This will be equal to, okay, better apply this. So, we can write like this, f of gx, no, first you write this one. Therefore, a to b f(x) and then gx minus gb dx, because this is monotonic decreasing and positive. So, by the Bonnet first theorem part, this will be equal to g of a minus g of b into a to xi integral a to xi f(x) dx, because this was the Bonnet's theorem. Bonnet's theorem says if f is bounded, integrable and gx positive and monotonic decreasing, then f of jx in gx is g of a into this. So, here this thing is monotonic decreasing and positive. So, the value of this at the point A into at some point a integral of a xi f(x) dx. So, this will come here, or now this can be written as integral a to b f(x) gx dx. This will be just arrange the terms, that is all, g of a integral a to xi f(x) dx, this term first, and then plus gb common, and then inside this we get a to b f(x) dx minus a to xi f(x) dx, this part. Okay. But this will be equal to what? This is equal to g of a to xi f(x) dx as it is plus g of b, and this can be written as integral, yes, integral xi to b f(x) dx. where xi lies between this, and that is what we wanted to show, is it not? That is the first part of this is f x g a monotonic, then we get g of a this part plus g of b this part. Okay. Now, in case if this is monotonic increasing, similarly if g x is monotonic increasing in the interval a b, the function g x minus g a is positive and monotonic increasing. So, by Bonnet theorem again, we have a to b f x g x minus g a dx is g b minus g a integral x I to b f x dx, and which implies the result, Okay. So, we get this thing, that is all. Thank you very much. Thanks. Okay.